Okay, I think I'm back. Sorry about this. So, actually, the hydrogen fuel cells are quite similar as a context, as a framework to a battery that we are using. And although most of us think that this is quite trendy or quite hype or quite modern, it was actually discovered back in the 19th century. Actually, it was discovered on 1838 by Symbian. So it's a rather old technology. However, we have only started recently we have started finding out uses for this technology, and actually found a more robust way to use it on a more on an industrial level rather than on a purely retail or commercial or private basis. So how does this work? We have the in this apparatus, as you can see it here, we had hydrogen coming in and oxygen also coming in, and then all the reactions create energy, and the outcome of these reactions it's simply water. Water goes out. Let's see a video that kind of describes how this is, how this works. A second. I've just sent you on the chat the link so that you can see, and just try to. Okay. So I want you to so what I want you to take from this presentation is actually two things. The first one is, of course, how this technology works, how hydrogen works, and the second is the feelings that most of the companies have these days, including large automotive sorry about that again. Large automotive producers and what they think of this technology. We're going to see later today what this technology, the economics of this technology are, and how they are compared to other similar alternative energy source technologies. So there is a lot of hype about hydrogen, and there is a lot of good vibes and good feelings that hydrogen might be the solution for our energy problems. Well, we're gonna see them. The basis, the perspective of this presentation is gonna be from the automotive point of view. It's similar throughout other contexts. However, from the automotive point of view, is quite advanced, this sort of technology, and has already proven or disproved itself in this context. And this is what we're going to be discussing today. Now, some benefits of this technology. Why are all these companies favoring or supporting hydrogen? Actually, there is a proven reduction in the burning of fuel cells. There is an improvement of the air quality because the emissions are quite low, if none, of air quality, especially in the urban areas, which is the most needed item in using fuel cells, hydrogen. There is a reduction of greenhouse gases, benefiting the movement against global warming. There is low noise and high power, and of course, there is a reduction in energy consumption. So it saves energy at the end of the day. However, when considering this, we have to start checking and we have to start addressing issues of total cost of ownership, not a specific subset of the entire hydrogen chain. Said that, we also have to start thinking of where we will be finding what are the sources for this raw material and how much does it cost to produce the raw material. And when I say how much it costs, how much it actually requires, how much are the energy requirements in order to produce the raw materials there. Now, there are a lot of problems there too. First of all, the costs. Although it has been already proven as a technology, the costs of producing hydrogen, energy based on hydrogen, is quite high compared to other energy sources. And sorry guys, the connection was lost again. Can you hear me now? let's go on. So, and especially what I wanted to tell you is that we have to start thinking of this cost problem in a more industrial level rather than on a private, on a retail level. For example, when we have a large cruise ship or a okay. When you have a large container ship or a large cruise ship, then it's so when you have a large container ship or a large cruise ship, we have to start thinking in a more in a bigger scale, in a more massive scale in terms of the energy requirements that are needed, as is the case when we are talking about container ships or when we are talking about large warehouses where the energy requirements are quite bigger. Another thing is the durability. Another thing is also the hydration of the system, the delivery of the energy. There are a lot of risks there. The infrastructure that is needed, and actually we need to start upgrading the infrastructure in order to accept hydrogen production facilities. The storage of both the hydrogen and the oxygen, as well as the energy when it's already produced, and the safety and precautionary issues there. Now, some examples that the energy has proven itself, of course, vehicles, bicycles, rockets, airplanes, buses, motorcycles, scooters, pretty much in all different areas of energy needs, the hydrogen sources have proven themselves. However, again, going a little bit back, when it comes to ships and the maritime industry, and the shipping industry more precisely, the needs are a little bit different. And this is what you have to consider when selecting and when addressing each system separately. Now, again, some introductory definitions and issues that you have to consider. First of all, we have two different main, actually, families of fuel cells. The first is the stationary fuel cells. This is actually a system of fuel cells that can generate water from hydrogen or natural gas as a fueling, and from oxygen in the air, and they produce as an outcome, as an output of this reaction, they produce electricity and heat. So this reaction is carried out in each of the basic cells of the fuel cell, and each fuel cell consists of an anode, a cathode, and an electrolyte, which all of them, all of these attributes, allow the charges to move from one side to another side of the fuel cell. So the electrons move from the anode to the cathode through an external circuit, producing the electrical current and thus powering the load. And then such cells are placed in a series so that we can reach the adequate voltage output. So when assembled together, the cells constitute an energy module of the required power known as the stack. You can see it here, how it looks like. We have this is one of the modules that we're going to be discussing. It's a solid electrolyte proton exchange membrane. Have the positive side, the positive electrode, and the negative electrode. Oxygen comes in and hydrogen, and then water is produced as well as the electric current. Sorry guys, I don't know what's happening. It keeps on dropping out the internet and closing down. So please bear with me. Now, said that, the fuel cell types are belong to these three categories. The first one is the proton exchange membrane fuel cells. The icon we saw earlier. We also have solid oxide fuel cells, and we have the molten carbonate fuel cells. So these fuel cells are actually classified according to the type of electrolyte they are using. In the first case, in the proton exchange membrane fuel cells, a proton conducting membrane is used as an electrolyte. So in pure hydrogen proton exchange membrane fuel cells, hydrogen is dissociated into protons of hydrogen plus and electrons on the anode. Protons are conducted through the proton conducting membrane to the cathode. As the membrane is electrically insulated, the electrons move from the anode to the cathode through an external circuit, producing the electrical current. On the cathode, oxygen reacts with the electrons and the protons, and they form water. Of course, these are the basic reactions there. It's purely sixth grade chemistry, or even earlier than that today. So such fuel cells operate at temperatures between 50 and 220 degrees Celsius, but typically they are on the range of 80 to 90 degrees Celsius. So other types of these structures also exist. For example, some of them are fed with a mixture of carbon dioxide and hydrogen. And the proton exchange membrane fuel cells are actually preferred for mobile applications. So these are, because they are easy to set up, they are not so sensitive, and of course they are cheaper. Now, the second family of type of fuel cells is the solid oxide fuel cells, which is actually ceramic material called Utria stabilized zirconia, which is used as an electrolyte. In these solid oxide fuel cells, oxygen gas reacts on the cathode with electrons, and they form negatively charged oxygen ions. And these oxygen ions move through the electrolyte from the cathode to the anode, where they react with hydrogen gas, producing electricity and water. Solid oxide fuel cells operate at higher temperatures between 800 and 1000 degrees Celsius, and they can be fed with fuels other than hydrogen gas, such as natural gas, for example, or any other type, or some other type. Sorry, natural gas is then reformed internally and converted to hydrogen. That is. The third family is the molten carbonate fuel cells, which is actually using lithium potassium carbonate salt as an electrolyte at very high temperatures above 600 degrees of Celsius. This salt melts and allows for the movement of negative carbonate ions from the electrolyte. On the anode, hydrogen reacts with carbonate ions to produce mainly water, carbon dioxide, and electrons. The electrons move then from the anode to the cathode, producing an electrical current. And on the cathode, carbon dioxide from the anode and oxygen react with the electrons to form carbonate ions. Molten carbonate fuel cells are fed with fuels other than hydrogen gas, or for example natural gas or any other gaseous type. And as in the solid oxide fuel cells, natural gas is reformed at the end of the reaction internally. So because of their high operating temperatures though, and because they're not that stable, they cannot be used as mobile devices, and they have slow startup times in order to reach the high operating temperature. And only they are used only to stationary applications, stationary stations actually producing in large warehouses, or they could be used in large ports. Now, hazards and safety measures. Fuel cells are low pressure systems, and upstream the fuel cell, the hydrogen feed pressure is reduced to low pressure, for example, 250 millibars, less than a bar at the cell's inlet of the Axane fuel cell compact. For example, this is one of the devices that are used, that are widely spread. So when we are talking about stationary fuel cell systems, most of them are free from hazards related to handling pressurized hydrogen. So it's quite robust when using hydrogen. However, since fuel cells are consisting, the structures there consist of a stack of basic cells in which chemical reactions take place. There is the risk of leaks, and this is one of the main risks, the main hazards in this operation, this activity. So in order to avoid the formation of flammable mixtures, we have to set up an extensive and robust sensor network that would be able to detect the leaks of this reaction of the hydrogen when we are using these structures. Now, once sensors have detected that the pressure of hydrogen, for example, at a specific place has a higher concentration than a threshold value set, we have to take isolation measures. And this is why we actually haven't used such energy sources so heavily so far in other modes of transport like the shipping or short sea shipping or whatever, because of these issues that have not been studied yet. Now, some standards. These are the standards that all the stationary applications have to comply with. For example, the IEC 62282 with fuel technologies. These are here, we will not be discussing those per se. I have just included all these standards in order for you to study them on your spare time, or if you decide to go on to this road using hydrogen, start studying all these standards. So we have the fuel technologies. What are the fuel technologies? What is the main terminology here? We also have the minimum requirements for safety and performance of fuel cell modules, which applies to all the fuel cell modules with alkaline, proton exchange, and so on and so forth, electrolyte chemistry. We have basic fuel cell power systems with regards to safety and the measures that have to be taken in self-contained fuel cell power systems, or fuel cell power systems comprised of factory masked packages and so on and so forth. We have the fuel cell systems. This IEC 62282-4 is the standard that pertains the fuel cell systems for forklift applications. Actually, forklift applications are some of the more robust applications that we are using these days in shipping, sort of speaking, value chains. So this standard pertains these applications. Additionally, similar to these forklift applications, we have other auxiliary systems that are based on similar energy sources and energy source structures. We also have fuel cell technologies for small stationary power systems as serving as heating appliances, both producing heat or producing cold, and this is actually what is needed in cold storage. For example, in let's say in a small cruise ship, the cold storage for the stores or for the food, with vegetables and stuff like that. We also have stationary fuel cell power systems installation guides, which provide the minimum safety requirements for the installation of indoor or outdoor stationary fuel cell power systems. This standard here covers the safety, performance, construction, marking and test requirements and the sustainability of fuel cell systems on board specialty vehicles and other auxiliary power units for transport value chain. And the last one here are fuel cell technologies for stationary fuel cell power systems, safety issues and safety precautions, which is partly covered by the ISO 62282. Basic considerations, then further on, basic considerations of indoor use of hydrogen standards. And last but not least, hydrogen detectors, the ISO 26142. Now, apart from the safety precautions and the general safety precautions actually, and the structures and the definitions, we also have a lot of standards used in describing the explosive atmospheres and actually what are the measures that have to be taken in this. Sorry about that, it stops recording sometimes, so it's a little bit annoying, I know, and I have to apologize for that. Now, there is a couple of standards, a set of standards describing the explosive atmospheres, what are the safety precautions, and what is actually the equipment that can be used or should be used in order to protect ourselves. So the part 1 through to 18 of the IEC 60079-1 gives all these definitions and explains more in detail what sort of equipment is needed. Also, there are the material characteristics for gas and vapor classification, the test methods and the data. It's actually the network of sensors that we were discussing earlier on. What sort of sensors are needed there. And the last one is the explosive atmospheres, the gas detectors specifically, and the performance requirements of detectors for flammable gases. Now, said that, we will go through a short case study of using and deploying fuel cell powered forklifts at large distribution centers of the USA Department of Defense. This is a case study by Michael Keynes back in 2013. And what he tried to do is that he tried actually to study the not only the effectiveness but also the efficiency and the cost efficiency of these systems. Now, these are the four project sites that were used over there. We have four different types of mobile actually and stable production. Now, the approach included gathering all the detailed cost data at each site from participating manufacturers, the on-site staff, and open source literature, comparing these costs against some benchmarks that they already had, and comparing them with alternatives that they could find. They also tried to address capital and operating costs, CAPEX and OPEX that is, and they try to analyze about 10-year forward looking of real costs without making any discounts. Well, that is, they try to make the analysis without playing around with interest rates and trying to make up things with the MPV. Now, let's see what they came up with. First of all, the cost categories that they consider. These are the cost categories that you have to consider when addressing these hydrogen production units. Infrastructure depreciation, infrastructure operation and maintenance, the space that is needed, the fuel source, what's going to be natural gas or water or whatever, and the power that is required in order to give sparkle to this system, that is. So in its case, they compared the cost of the delivered H2 energy source. Now, with regards to the fuel cells, what were the cost categories that they considered? The forklift depreciation, the forklift operation and maintenance, and the spares and the servicing of the forklifts. Also, the fuel cell operation and maintenance, including the spares and the servicing, fuel cell refueling labor time that is needed, the hydrogen infrastructure operation and maintenance, the infrastructure space cost, and the hydrogen produced and delivered. Now, some more cost categories for alternative energy sources for batteries and propane, that is. In the case of batteries, they try to come up with figures regarding forklift depreciation, forklift operations and maintenance, battery depreciation and operation and maintenance, charger depreciation and charger operation and maintenance. That's one of the biggest cost elements in this case, in this analysis, in this study. The power that is needed to recharge the batteries, the battery change labor, the infrastructure operation and maintenance, and the infrastructure space cost. Also, with regards to the propane, the cost categories that were considered was the forklift depreciation, the forklift operations and maintenance, the fuel, the price of the propane is, the infrastructure depreciation, the infrastructure O&M, the infrastructure space, and the refueling labor. So as you can see over here, they try to come up with relevant figures from all the different sources so that they could produce a level playing field along all the different systems that they were analyzing, they were exercising there. Other factors that were also considered are non-economic actually factors, including the reduction in the hydrocarbon emissions, the reduction in greenhouse gas emissions, the enhanced work productivity with fuel cells, the DoD leadership in national energy effort by creating a market opportunity for fuel cell technology. That is the branding actually that the DoD wanted to put on forward. And the development of a transport option that might have value to DoD and others in the future. So they try to consider the wider social implications that this new technology had. So the thing here is, of course, you can all understand that in the first case we have solid figures that we can assess upon quantitatively, and in this case we have more of a qualitative assessment that can be borne. So no matter what the hard figures you might come up with, if the leadership really wants to invest or really wants to adopt this new technology, then you cannot really go by this decision. But anyways, we will see what happens there, and we will see what are the key drivers there in this decision. Now, we can see that the cost of producing the H2 and the cost of delivering the HQ is different in its case. And for example, in one of the sites, the DDWG, which had a steam methane reformer, the cost of producing H2 was about $22.4, and the cost of delivering the HQ without counting any system losses was $22.5 a kilo. So we can see that there is a difference, a big difference between cost of producing, and this goes along with the rest of the figures there. There's a difference between producing and delivering, so there are a lot of systemic losses over there that we have to address and we have come up with. Some conclusions from producing hydrogen in these places. So going in, the production of H2 from natural gas was thought to be the least expensive option. However, there were a lot of technical limitations that increased the final cost of this option. Producing hydrogen, the second thing was that producing hydrogen from waste gas is a better concept. However, in practical terms, it was very difficult to be implemented. And last but not least, the production of H2 via electrolysis was the most economic option compared to the cost of importing H2 in a gaseous form. Why? Because the electrolyzer ran a high percentage of the time. So sorry, we'll talk about this in a bit. It was expensive to import gaseous H2 because of the high cost of transportation and the experiment associated with with photovoltaics production of electricity, but that was treated as a separate investment in this system. Now, what I wanted to say is that you can see here that the level of utilization, the percentage of utilization of the system plays a very, very important role in assessing the system. It all comes down to how much time you're really using the system. So if you have, let's say, a small warehouse and you have a couple of forklifts or whatever, and you will be using your hydrogen production facility for a couple of hours a day, then it has a lot of fixed costs, or this entire structure has a lot of fixed costs, and you would end up paying a lot of money upfront for this investment without ever being able to take this money back. So you have to compare the utilization. You have to run this system as efficiently as possible. And that's the second thing, that when they tried to compare different solutions, over here, the cost of transporting gaseous H2 is higher than, for example, the cost of transporting, I don't know, water or whatever. So all these different elements in this cost structure came up with a different figure, and then this would come up to a different factor in your analysis. You have to consider all these different practicalities, all these localities in your assessment, in your impact assessment, and see what is the best, the fit for purpose system that you will be suggesting or proposing. Now, that's a comparative cost table for fuel cell and battery forklifts for a sample site. We can see that for this period, the fuel cell forklift, the cost for 40 forklifts would add up to $155,000. The fuel cell forklift with cost reduction product program, a sort of alternative for fuel cells, was $119,000, $100,000, and the battery forklift was 68. So we can see that the over here the cost of hydrogen infrastructure plus fuel cell upkeep is too high for the fuel cells to be economically competitive. I mean, look at the figures over here. We can see that the fuel cell forklift is more than double the battery forklift. However, again, going back to the previous argument that I've made, it all depends on how you consider the system. What is the utilization of the system? What's the utilization of the energy production facility? What are the rest of the reductions that can create some positive impacts on fuel cell production? And of course, another thing, and now this reminds me of the entire debate in the photovoltaic area, that this is a production methodology. Production, it's a system that is very early in the learning curve. That is, that it's very expensive yet to produce fuel cells. In 10 years' time, this curve will be lower. It will be easier and cheaper for us to produce fuel cells compared to what is the cost structure today. And actually, that was the idea, and that was the case with photovoltaics. 15 years ago, it was also expensive to produce energy from solar panels. Today, it's about a fourth of the original cost. Now, extrapolate this to an entire system. That was the vision 15 years ago. That was the vision from the European Commission to have entire areas, surfaces full of photovoltaics producing energy. Now, the whole idea is that back then it was the cost was something like, especially for smaller installations, the cost was something like 3.5 to 4 euros per kilowatt in order to produce in order to install this facility. Nowadays, it's closer to 1.5, 1.4. So you can understand that the cost of installation has dropped dramatically, as is the production capability. I mean, today, the same surface for photovoltaics uh, can produce up to 3 times more compared to what the production capacity was 8 years ago. So you can see how all these systems evolve through time. And this is why we can see here that the fuel cells used in the forklift case cost twice as much as the old battery forklifts. Actually, the battery forklifts are out there for 30, not 30, even 40 in some cases, years. So you can see that the system is out there for 30 or so years, and the fuel cell systems are out there for less than 10 years. So you can see this learning curve where the systems are. Now, in another case, we have similar differences. For example, in this production facility, the DoD product warehouse, the fuel cell cost for 19 forklifts that they were using was $130,000, and the propane forklifts, their equivalent, was closer to $80,000. We can see that it's almost twice, not twice, it's almost 1 3/4 of the cost of propane forklifts. Again, though, the thing is that the propane forklifts, the propane production facilities, structures are out there for more than 20 or so years, and you can see this difference in the costs of the systems. Again, the conclusions from this one are that the fuel cells are not that competitive with propane when used with propane. And the other thing is that propane is relatively inexpensive because it requires little on-site infrastructure, if any. And the other thing is that the cost of propane, and generally the cost of these sort of energy sources, the price has been reduced quite dramatically for the past couple of years. So it's even more competitive to use these systems. However, now going back, you have to compare quite many more things, issues when doing this analysis. For example, the propane-based forklifts are more risky compared to fuel cells. The hazards of explosions are quite more, and the consequences are more dramatic compared to fuel cell explosions and stuff like that. So these are more issues that someone has to consider before making any arrangements whatsoever. Now, again, some more conclusions that came up with were the utilization of the system itself, as well as adding more elements to the system, trying to utilize as much time, production time from the fuel cell production as possible. It goes back to the argument made before. All these issues and all these metrics have to be carefully considered before making any making any conclusions or any commitments to the system. Now, some overall conclusions from this study. Fuel cells were not economically competitive in any of the four experimental projects, and these results were actually expected. However, the relative attractiveness could be increased by the following drivers, and these are the drivers that you can start manipulating in your analysis in order to see what's more economical, or these are the drivers that will make or break your proposal or your system. The first is the intensity of the use, the utilization, the increasing of the number of forklifts using actually fuel cells at each site, the downsizing as much as possible of hydrogen infrastructures to more closely match the demand that is needed. You don't need to go for extra capacity when you don't really need it, because the costs increase exponentially in these cases. Accepting more of the risk of infrastructure failure, of course, and this goes along to other incentives that might be given to a specific company by the government. In this case, the government could or should or would subsidize the production of fuel cells. The same issue exists in the European Union, where the European Union subsidizes directly or indirectly alternative energy sources. Well, in the case of photovoltaics, for example, it's the FIT, the fixed tariff, the fixed feed-in tariff that is used. Similarly, in the shipping sector, the late Marco Polo 2, the Motors of the Sea nowadays, part of the TEN-T program, subsidizes heavily alternative energy sources for the shipping sector. And even national initiatives in each of the European Union member states also subsidize heavily alternative energy sources. And of course, there is a certain trend with the ports these days to give to supply green energy to the ships, the cold ironing of the ships. And this green energy usually comes from windmills, photovoltaics, hydrogen, and so on and so forth. So you can see that there are a lot of incentives that could be taken as an advantageous form of making up for the cost of energy supply. This goes along with longer-term contracts with specific companies. By the way, in the shipping sector, this has taken the form of cold ironing for the ships, or energy supplies for refrigerated containers directly from the energy producers in its member state, in its country, in its EU country. So when you have the refrigerated container, for example, sitting in the port area, then you can go and buy energy directly from the producer, instead of buying energy from the port, or having the container producing energy on its own. So there are a lot of schemes there that can prove themselves to be more beneficial. However, this also has to be again carefully considered and carefully assessed. And of course, last but not least, all the tax breaks that are given from all of the member states for producing more energy friendlier sources are also something that has to be carefully considered in this case. Now, we are going to discuss. Oh, would you like to break? I think it's more than an hour that we are talking. Would you like to have a short break now? Okay, let's have a break and we'll be right back. Okay, let's continue. Now we'll be discussing now in this section of the module, we will be discussing some safety issues and safety precautions. This is going to be rather a practical case, a practical discussion rather than a purely theoretical. We're going to be seeing a lot of daily precautions, simple precautions that you should take in order to come by risks and come by hazards related to the fuel cell production. Now, some safety issues, an introduction, simple introduction. First of all, you have to size up the scene, what's going on there. Try to understand, try to put yourself together over there and see what's going on. You have to identify early on the hydrogen, where is the storage of the hydrogen and the production where it takes place, taking some initial protective measures up and trying to first of all protect yourselves and protect the other people over there. Detecting gases or a liquid hydrogen release, detecting the hydrogen flame and responding to fire and combustion. Now, some hydrogen related safety precautions. First of all, you have to secure the equipment. Then you have to go and rescue passengers and people that are out there. We will be also discussing about some personal protective equipment that you have to bear, you have to have. And we will also discuss about some emergency response diagrams and recognizable causes to hydrogen related incidents. Now, personal protective equipment. Of course, it goes without saying that when an incident, a hazardous incident, you come up with, you have to wear all your PPE, especially in order not to have any accident yourselves, any injuries yourselves, or any catastrophic accidents, including fires, vehicle fires, accidents on the personnel, accidents involving fuel cell vehicles, and so on and so forth. Additionally, because the flame, as we're going to see a little bit later on, because of the flame, the hydrogen produced flame is very difficult to be recognized, be seen, especially during the daylight. Thermal imaging equipment is also needed in order to detect it. And of course, you have to have your hands and your hand tools insulated in order to avoid igniting any hydrogen gas. And of course, the standard firefighter turnouts and respiratory protection are in any way necessary when working on an incident where hydrogen leaks or fire occurs. And if the incident itself involves liquid hydrogen, you have to wear thermal protective clothing too. That's a very crucial thing, a very important issue there. Now, non-static equipment and tools are required. Why? Because in leakages, hydrogen cells are quite, and we're going to see that later on, are quite explosive. And of course, if you also add up the LNG, that is one of the raw materials to produce fuel cell energy, is also even more explosive. So all of the people working into such environments, they have to wear non-static equipment, and all the tools have to be insulated from static electricity. That also pertains fire extinguishers, fire blankets, brooms, pretty much whatever you will be using there has to be insulated. Now, wearing jewelry, rings, necklaces, all that stuff are strongly discouraged, as most of the bibliography says. Why? Because these might bear static electricity and might produce the ignition for the explosiveness of hydrogen. And equipment also provides firefighters with the essential protection, and all those working there, that is, with the essential protection that is necessary from the potential of electric shocks, flammable explosive gases, hazardous fumes, and so on and so forth. By the way, we're going to see that also later on, but the power that is needed to produce energy from fuels is, for example, in vehicles or in forklifts, is higher compared to traditional energy sources. For example, in traditional energy sources, you have 12 volts or 24 volts, and that's the maximum. However, in hydrogen powered systems, the voltage might reach more than 50 volts, which actually the 50 is the threshold where you can have a heart attack. So you can see that if you're not insulated enough, you might be electrocuting yourself when trying to handle equipment in such an environment. So you have to be very, very careful. You have to wear all the protective equipment in order not to harm yourself or in order not to harm anyone else there. Now, additionally, personal protective equipment that should be borne in a hazardous environment includes self-contained breathing apparatuses, coveralls, turnout pants and turnout coats, fire-resistant gloves, of course, high-voltage rubber gloves, and that's very important, especially in stationary stations where the energy, the voltage is quite higher compared to other stations. Boots, steel toes and shanks are also necessary. Helmets, face shields, and in some cases where we have leakages of poisonous or other sort of material, in cases of hazmat that is, you have to have hooded chemical resistant clothing. That is the two-piece chemical splash suits, the disposable chemical resistant overalls, and the disposable chemical resistant boot covers. So all of that are quite necessary when an incident occurs. Now, some hydrogen safety facts. Of course, safe handling. In order to handle safely the equipment, you have to wear safety glasses with a well-ventilated area, so they should cover entirely the eye area of your face. Emergency for the eye or the skin, generally speaking, it's not a very crucial factor, although some protective equipment, as I said before, should be worn. And in cases of inhalation, you have to understand that hydrogen on its own is not poisonous. However, if a room, an area fills up with hydrogen quite quickly, hydrogen tends to remove all the oxygen, all the air that is needed for you to breathe, thus producing an asphyxiated environment over there. So accidental inhalation, you have to make a note that accidental inhalation of hydrogen might cause some breathing problems, especially to elderly ones. But it doesn't really cause any problem on its own, the simple inhalation. That's why it is always recommended for you to move to a well ventilated area. And when breathing has stopped, of course, you have to move on and do some CPR on these persons. Now, general hazards and risks for the hydrogen storage. Hydrogen is capable of migrating through small openings, so even small cracks on the equipment will release the entire oxygen inhalt of the container. The main concepts there for the emergency responders. So if something happens in a warehouse that you could be working, or on a ship, on a vessel, or on the port, is that you have to protect yourselves from electrical shocks and from flammability of the fuel itself. Other additional concerns might include cryogenic burns and asphyxiation. For example, the cryogenic burns, you will see later on that on cracks, on certain cracks, you can see when the hydrogen is released, you can see a snowy-like area, a frozen area around the crack from the low temperature of hydrogen. This can produce cryogenic burns, which are treated, but it's not a good thing to have actually. And of course, asphyxiation, we talked about asphyxiation earlier. Now, venting of stored hydrogen may also be the best means of mitigation, ventilating that is a situation, as long as the area is free from ignition sources. So you have to be very, very careful on the situation over there. If there are any ignition sources whatsoever, you have to be extra careful in the ventilation. Hydrogen will dissipate very quickly and will combine with oxygen to form water. So these are things that you have to consider in order to attack a leakage of hydrogen. Now, how to? Easily said, you have to actually eliminate all ignition sources. So no smoking or no open flames or no ignition from wires, stuff like that. You have to keep all your tools and all the equipment in good condition, and you have to use only non-sparkling tools. For example, you will not use any cutting machines that produce sparks there. So you have to be very careful to use not only the correct tool, but also the correct size for the tool in order to loosen, tighten, or tighten the hardware. Now, another thing is that you have to wear non-synthetic clothing, so nylons and stuff like that are a no-no. Ordinary cotton or flame retardant cotton or any other similar clothing is of course preferred. And the electrical equipment must be explosion proof and intrinsically safe for purged. So all of the equipment has to be very carefully selected in those areas. So you have to be very careful in addressing the specific risks and selecting this equipment. General hazards and risks for tanks and cylinders. So liquid hydrogen tanks are always emit small quantities of hydrogen if the hydrogen is not oxidized or burned off in a controlled manner. So you will always have that, and this is why you have to be very careful in selecting all the different subsystems, substructures in order to burn off or oxidize the hydrogen that is leaked. All hydrogen-containing fuel systems have a great propensity for at least small leaks due to the pressure of the gaseous hydrogen and the small size of the molecules. So, unfortunately, at the end of the day, there is no, at least for now, there is no such a structure that can restrain, can limit small leaks. We don't know how the technology is going to evolve, but for now there's no such system. This is why you have to be extra careful in the areas where the transfer of hydrogen is taking place. And this is why we discussed earlier in the case of the DoD, the necessary space for the infrastructure that you're going to be developing, you're going to be building up your system, your container system, it has a certain amount of cost because it has to be distant, it has to be covered, and it has to be protected from the rest of the warehouse, for example, in that case. Now, because of the high dispersion rate of hydrogen, small leaks would likely pose a problem in rare instances, but this usually takes place in unvented or very tight or small individual garages or warehouses or storage rooms. And again, going back to the previous argument, this is why all the transfer facilities and the storage facilities are quite away from the main operations, the main theater of operations for the production facility, in order to keep away all of these factors that could produce a sparkle or ignite or generally increase the risk. Now, safety concerns in larger unvended private or public parking garages for the case of cars which are more it's a more often production facility these days, will be more of an issue. For example, public garages in malls have an issue. Now, comparing these to shipping systems, RoRo ships have a higher risk, as is the case of small energy production facilities in small container ships and small cruise ships. But then this is something that you have to acknowledge and you have to take care of. Now, some general precautions there. You have to be very careful so as not to crack open a hydrogen cylinder to clear the valve of dust over there. Why? Because always there is some hydrogen leftovers in the cylinder, and these leftovers may ignite. And this is one of the cases that actually increase the risk, the daily risk. Another thing that you have to consider is to never drop, drag, or roll, slide, or handle in any other way rather compared to the designated way the cylinders. As far as the wrenches, you have to be very careful never to use to open or close a valve on a cylinder, and you have to use only strap wrenches to remove over tightened or rusted caps on the cylinders. And last but not least, you also have to group of cylinders that are burning. You have to group them together and keep the firefighters and the personnel that are dealing with this, keep them in a distance. And of course, when an explosion occurs, you have to protect yourself from fragments or sorry about that, we stopped again. Now, what about the valves, the leaks, and the PRTs, the pressure relief equipment? Hydrogen systems include high and low pressure fuel lines, so you're gonna have high and low pressure fuel lines, and you have to be able to recognize which is which. Of course, you should not mess with any of them, but if need be, you have to put extra care on the high pressure fuel lines. They are equipped with pressure relief devices, all of them, and similar structures, so that the environment is safe enough. And the location of the PRD devices depends on the type of the system. You can easily understand that there is no standard, any standard location whatsoever. For example, in cars, These are mounted on the boot of the car. However, again, this may vary, and you have to be extra careful in order to recognize where this is, so as not to mess around, to be more careful in there. For example, you should not make any actions that would ignite or produce sparkle during near a PRD device. Now, hydrogen leaks generally originate from valves, flanges, diaphragms, gaskets, and other various types of seals and fittings. So you have to be extra careful there too. And for leaks that are relatively small and controllable, you have to use the shut-off valve. But for leaks that are uncontrollable but quite large, you have to try to shut off the supply source. If this cannot happen, you have to evacuate the area in order to protect yourselves. Now, indicators. For compressed hydrogen, a loud hissing or a shrilling with a PRD release and a concentrated flame of stream is apparent there. For liquid hydrogen, a fog or a cloud formed around the cryogenic hydrogen storage tank is apparent. Uh, you can see, for example, ice crystals that are formed around the storage tank. This is a very good indicator that you have a leakage. Now, liquid hydrogen poses greater risks than compressed hydrogen because it's actually cryogenically reduced its temperature, and this can induce personal injuries on you. Now, hydrogen, when stored as a liquid, it is usually stored at minus 253 degrees Celsius. So it can, of course, cause not only cryogenic burns, but it can damage your lungs. So you have to be extra careful there. Detection sensors and personal protective equipment are quite critical when handling liquid hydrogen, and properly working ventilation equipment should be in place and should be regularly tested for its working conditions. It has to be working well so that all the hazards can be minimized. Now, precautions. You have to eliminate any source of ignition and, if possible, remove cylinders from the area that there is a problem to a remote, preferably outdoor locations away from possible sources of ignition. So you have to transport to get the cylinders away from the area that is problematic. Then you have to ventilate the area properly. So that's another issue for those developing some such systems. You have to have in place not only the stable ventilations, static ventilated facilities, but you also have to have some mobile ventilators in order to ventilate the area properly. You have to avoid skin contact with liquid or cold boil of gases. Of course, this goes without saying for reducing the personal injuries. And you have to be careful not to enter the area that contains flammable mixtures. For example, LNG mixtures should be avoided entering these areas. And last but not least, you have to avoid spraying water on pressure relief devices or gas ventilators. Now, as we said before, hydrogen is an asphyxiate substance. In rare instances and in closed spaces, it can displace quite quickly oxygen, and this causes, of course, oxygen deficient atmospheres. and this in turn disables you from being able to breathe correctly, properly. Precautions on that: always open a compressed gas cylinder valve slowly to avoid rapid system depressurization or pressurization. And in order to understand whether you have entered an environment that is full of hydrogen or it's an asphyxiated environment, uh, you might have some headaches, or drowsiness, or dizziness, or excitation, or excess salivation, or vomiting and unconsciousness. If you feel like that, you know that you're on an asphyxiated environment. Now, some general hazards and risks for hydrogen powered vehicles. The two main dangers from fuel cell and hydrogen powered vehicles are the electrical shock and the flammability of the fuel. Actually, this is not only the case in the hydrogen vehicles themselves, but it's the same case in producing energy in similar facilities in ports, in ro-ro ships, in cruise ships, and pretty much everywhere that is powered from hydrogen. So we said that the main risks with hydrogen-powered structures is the electrical shock and the flammability. We've said that the traditional systems, the traditional vehicles are using 12, 14, or 28 V systems. However, the hydrogen powered operate on more than 50 volt systems, and most of them some of them are even using higher voltages like 200 to 400. It's similar to the installations that we have in our homes. Actually, the voltage itself is not the only issue. The second issue is that these systems also have a high ampere intensity on the currents. So it's even lower, lowering it at 50 or 60. Most of these structures these days use 50 to 60 current inputs. However, being and having higher intensity power currents over there, this is very dangerous for personal injuries. By the way, the human heart stops at a 50 volt. I don't remember correctly, but I think it's a couple of amperes, the intensity of the power, if I remember correctly. So you can understand that there is a high risk of electrocuting yourself if you go and try to tackle a hydrogen powered facility or structure in general. So you have to be extra careful on what is going on and be extra aware of the dangers and the risks. Now, another thing is the hydrogen's flammability, which range is wider compared to other fuels. So you have to be extra careful. Don't say to yourself that, gee, I'm not that close over there, so I can be safer. The flammability range is wider. And of course, you have to pay certain attention, because there are other fuels that are also used to power fuel cells, which include methanol, ethanol, methane, generally all these LNG, LPG structures. So you have to be extra careful, because it's a more powerful mixture, the ones that they are using in hydrogen production. Now, fuel used to power a vehicle does not necessarily have to be stored on the equipment as hydrogen. So that's another issue there. And also you have to consider that reforming the different hydrogen sources, such as alcohols, methane, propane, and so on and so forth, or even regular gasoline or similar mixtures, it creates gaseous hydrogen in the vehicle itself, and this can explode with a simple spark over there. That's why we are suggesting that there is a lot of risk. There are a lot of hazards there in trying to assess the situation and protect people and equipment. Now, emergency procedures. First of all, you have to size up the scene. What is the situation? What are the problems? What are the risks? What are the hazards? What's going on in there? Do we have a car that is that has caught fire? Do you have a forklift that has exploded and there is a leakage? Is there an installation, a facility that produces energy from fuel cells and it has a strong leakage? You have to assess what the situation is. And you have, in this assessment, to identify hydrogen in either commercial, transport, or stationary facilities. So you have to see what's going on over there. You also have to identify vehicles that are powered from hydrogen. And you have to start taking the initial protective actions, the initial protective measures. Now, detecting gases or a liquid hydrogen releases the next step. And you also have to detect whether there is a hydrogen flame. And this is why we said in the beginning that you have to have a thermal assessment equipment, because in most of the cases, and especially in the broad daylight, you cannot really see the hydrogen flame itself. Now, the next step is to secure the vehicle in the case of a hydrogen vehicle accident, and you have to call for fire and combustion responses, firefighters that are specifically trained for responding to such incidents, in case there is such an incident, that is. And of course, you have to start pulling out the passengers or the employees from the vehicles or the structures, if you can. I mean, if you have all the protective equipment and if you have gone through the different measures and the different assessments discussed before, you can start extricating the passengers from these areas. If not, you have to wait for the specialized personnel to do that. Now, some ideas and some issues there. First of all, when sizing up the scene, do not rush in. Take a couple of moments to think what is going on over there, and then try to help and try to offer a hand to those people in need. The position responding units, the fire trucks, police cruisers, ambulances, and so on and so forth, have to be placed upwind and away from leaking hydrogen or PRD ventilators, obviously. All these trucks, these cars, are producing sparks over there. So you have to be extra careful not to induce any sparks when you have an emergency like that. And now, regarding hydrogen fuel cell vehicles, in case of spills from high voltage battery packs, you also have to contact the hazmat groups directly. Oops, sorry. Now, identifying hydrogen in commercial transportation, some signs there that can help you recognize hydrogen. First of all, the placards and the other markings are required on bulk shipments and also on containers and on installations and facilities. And said that, you have to recognize that this is not a nice to have marking. This is required by law. If an installation doesn't have such markings, then you will have problems, legal problems. And of course, in case of an accident, the entire blame is put back on you. Actually, the markings are there to help all the emergency responders easily recognize what the material is and respond accordingly and appropriately in any event of an emergency. And this holds true not only for the emergency responders themselves, but additionally on the hazmat teams. For example, if you have a leakage, the hazmat teams can understand quickly and assess efficiently what the leakage is, what the issues are going to be in terms of protecting the environment, and select all those tools and all these mechanisms in order to protect the environment and protect life. Now, we can see here, these are the two different, well, it depends on the marking itself, but it's quite the same one, two different markings for the hydrogen in commercial transportation. And in fueling stations, these are the markings that are used. So you can select one of them, one of these markings there. Again, for those of you that will get into the establishing, the developing, and the implementation of such facilities, you have to go through the latest developments in DG, dangerous goods markings, either the IMDG, the IMO's dangerous good markings, or any other relevant system that can or should be used. Some initial protective actions when you arrive there or when you see that something bad is happening. So when you approach an incident, keep all the unauthorized personnel away, isolate the area, and try to stay upwind or against on the other side of the leakage. Try to listen for venting gas and watch for thermal waves that would signal hydrogen flames, hydrogen-related flames, so that you can, first of all, protect yourselves and the personnel, and also notify the emergency responders. Follow all the standard operating procedures that are set up, and you will be trained or you will train someone else. And eliminate all potential ignition sources, even try to keep unauthorized person, even trying keeping unauthorized personnel away for eliminating these ignition sources. And of course, last but not least, be aware that hydrogen fire is when hydrogen fire is detected, you can, if you assess it in this way, you can allow it to burn itself off. And if you can protect all the adjacent structures, the similar structures that are in the area, so if you can protect them, you can leave it to burn off. You can leave the hydrogen fire to burn off itself, and then the emergency responders can step in. Now, detecting the gaseous hydrogen release. Hydrogen gases are colorless and odorless, and unfortunately we cannot really sense it. And this is why we need specific structures in order to understand it, in order to recognize these releases, and in order to cope with these releases. First of all, the first responder should listen for sounds of high pressurized gases escaping from the ventilator or from cracks of the container. If this is the case, you have to respond accordingly. Otherwise, another thing is that another option is for you to use commercially available thermal conductivity sensors or catalytic combustion sensors or electrochemical sensors. These are all apparatus sensors that can be used in order to recognize whether you have a leak, where this leak is, and whether you have a flame and where this flame is. Now, gas and flame detectors, they can be permanently installed in storage facilities and fueling stations. However, you can have, as we said before, you can have mobile apparatuses that can be used in its case, in its specific case. And last but not least, regarding vehicles, when it is safe to do so, if you can, what I said before, step back, listen first, and then if you can hear any hydrogen escaping, the sounds, the hissing, the thrilling of the sounds, or if you can look for frost around the PRD ventilator or the crack, then try to do those things first in order to assess the situation. Now, a leaking liquid hydrogen container may have frost or ice crystals, as we said, on the outside. You can easily see that and you can easily spot it. Small spills of hydrogen disperse rather quickly, so you have to think that any spill should be considered as a potential fire hazard, and any spill whatsoever might also induce flames, as you said before, and this is how you should approach such incidents. Larger spills, on the other hand, cause the ground to be frozen. So larger spills do not vaporize quickly, so you have to be extra careful in these cases. As we said, cryogenic burns in these cases are quite often, and personal injuries can happen in no time in this case. Now, if this happens, you have to evacuate the area until the spill itself has dissipated itself, and you only use water sprays to reduce the fog that is produced, and diffuse the vapors, and that's the only thing. Clouds of gas may quickly, and this is in case of a spark over there, may quickly become huge fireballs, and the results, you can all understand, that are quite tragic in this case. Now, what you can see here is a liquid hydrogen release. You can see the fog that is produced, and below the fog, you cannot really see that in this icon, but the ground is frozen. It's actually frozen, and all the devices, the surrounding devices, are also frozen. So you have to pay attention, because even in dry climates, the liquid hydrogen spill will create clouds and fogs like that, since the condensed water vaporizes, and since the hydrogen warms, it will dissipate and rise rather quickly. Now, flames. Hydrogen burns with a pale blue flame that is nearly invisible in daylight. The flame may appear yellow if there are impurities in the air, like dust, sodium from the ocean spray, etc., etc. And a pure hydrogen flame will not produce any smoke whatsoever. Last but not least, hydrogen flames have also low radiant heat, unlike any hydrocarbon fire that you may not feel, where you may not feel heat until you are very close to the flame. So this is why you have to be extra careful, and this is why you have to have a lot of sensors on place and in place, in order to see whether something wrong is happening. Be extra careful, because all these, and especially the hydrogen related production facilities, do not give out any signals easily, but you have to be extra careful in order to not to produce any injuries on your own. When approaching a hydrogen vehicle that has been involved in an accident, immobilize, stabilize, and disable the vehicle. And you have to approach the vehicle at a 45-degree angle when possible, in order to help avoid direct exposure to a pressure relief device release. Now, we've seen that before. securing the hydrogen vehicles, it is essential to locate the PRD, the pressure release device ventilator, before beginning any operation on a hydrogen vehicle. You have to stop, and that's the main issue actually in responding to such incidents. You have to stop and you have to make quiet in order to listen for venting hydrogen and watch for thermal waves that could signal a hydrogen flame. In this case, and in most of the cases, you can see that these are on the back of the car, these PRD devices. Now, if safe to do so, try to isolate the high pressure hydrogen and high voltage systems by turning the ignition key off, or try to isolate the power source in the production facilities. It may take a couple of minutes for the electrical system to completely discharge, so don't go there quickly and start messing yourself around, especially if you don't have protective equipment on you. Once the vehicle is turned off, the high pressure systems are isolated. However, be very careful, because when systems fail, then it might signal itself that the system is isolated, but in real life this could not be the case. In reality, this could not be the case. Now, simply turning off the key closes the high pressure and hydrogen gas tank. However, fuel lines from the tank to the engine takes approximately a couple of minutes to get isolated. However, in any case, they still contain an amount of hydrogen. Now, regarding hydrogen fuel cell vehicles, it is essential to identify both the main as well as the auxiliary electrical system over there, and you have to refer to vehicle emergency response guides in order to identify high and low voltage systems, which are which, so that you can cope with. The high voltage battery packs must be disconnected from the electrical system in order to protect the rest of the system. And in order for you to do that, you have simply to remove the high voltage service disconnector. And to remove this switch, turn it counterclockwise and lift it out. Refer to vehicle emergency response guides to determine the specific locator of any switch whatsoever. And this now gets us into the issue of proper training, especially when you have larger facilities like storage facilities in ports, or refrigerators, or similar facilities on ships. You have to train very, very well the personnel in order to be able to cope with such incidents, in order to be able to address these issues. Fire and combustion response. The best way to handle a hydrogen fire is to let it burn itself off, of course under control, until the hydrogen is disappeared and burned off. Small fires can be extinguished with carbon dioxide or water sprays. However, larger fires may be controlled with steam and or nitrogen firefighting mechanisms. Now, if a fire is extinguished before all the gas burns off, watch for pockets which may suddenly reignite. So watch for areas that there are hydrogen leftovers or mixture leftovers, because small sparks may ignite it again. A hydrogen flame is invisible under many conditions, so you have to be very careful, very careful. And since burns may result from unknowingly walking into a hydrogen fire, hydrogen flames cause little damage from radiation, so there's no great risk there. Hydrogen flames can burn in a strong wind and be stretched out away from their source by a significant number of feet. And tanks containing hydrogen should be cooled with water if they are near a fire. Pipeline fires where shut off is possible and with flame characteristics of a jet or torch can be effectively controlled by slowly reducing the flow of hydrogen feeding the fire, or when the jet is small enough to be approached, put out the flame with carbon dioxide or dry powder extinguishers, or closing it off, closing the supply of hydrogen off completely, or ventilating the area thoroughly. Unusual fire or explosion hazards from reignition, as we said before, is present and should be extinguished, should be minimized without shutting off hydrogen. And for hydrogen vehicles, if the hydrogen system can be isolated, put out the fire with traditional means, but if the hydrogen system cannot be isolated, let the fire burn itself and it will burn off. Unfortunately, that's the only correct approach. Concentrate on keeping the fire from spreading onto other areas or neighboring objects. Now, pulling people out, extricating people, never cut into the hydrogen fuel lines or the hydrogen storage tanks or the PRD ventilation lines. For hydrogen fuel cell vehicles, do not cut the electrical cables of the battery pack. Now, that is a car. This is how a hydrogen-powered car looks like. We have the pressure relief device on the back of the car, the hydrogen tank, the high voltage battery that is needed, the fuel cell system in the hydrogen lines, the fuel cell stack, and the powertrain of the car. And you can see how this looks like. Similarly, mobile structures like this are also used in ships. And this is the end of this session. If you have any questions or any issues or any ideas, feel free to send us an email. Will be at your disposal. We will be discussing all things up. That's all for now. We will continue on tomorrow and the rest of the days. We didn't discuss anything today about risk management and how to approach from the academic perspective. Professor Zanatos tomorrow will be discussing more on the theory behind the assessing the risk themselves and all the different methodologies that are used in order to make a formal assessment of the environment. This is why this training module was intentionally made to be more practical, to see the risks, the everyday risks that arise from using hydrogen. Tomorrow you will be discussing with Professor Zanatos and with Theodoris Styliades, you will be discussing of these methodologies. And we will also move on Friday, if I remember correctly, the schedule. We will also have a mock assessment of similar systems. So, thank you very much for being here today. Looking forward to our next session. Everything is going to be uploaded on the TrainMoS site. So, thank you very much. Bye-bye.